Hi, welcome to the video Intel 8085 and Zilog Z80 timing. What do I mean with timing? How fast will the program run? That depends on the clock speed, CPU type, speed of the peripherals, and of course it depends on your code. Why bother with timing? The good news is you don't have to. And the bad news is, maybe you have to. Timing is mostly used in two cases. The program runs too fast, or the program runs too slow. What do I mean with it runs too fast? I hear you saying, the faster the better. True, but sometimes you want to have a delay, a small pause in your program. Like, hey CPU, wait for half a second. There's no such an instruction. This kind of CPUs can't sit still. They will always run at full speed. Even in the hard mode, they will do a no operation in a loop. For example, you have to do an asynchronous serial communication with a device, and you don't have a serial input-output chip, nor a timer counter or a clock chip. In these kinds of communication, the timing between bits is essential. You have to keep the CPU busy until the desired delay has elapsed. The program runs too slow is more apparent. You have to optimize the code if possible. Or the CPU should only be interrupted for a short time, like in an interrupt routine, especially in a video or sound routine. Otherwise you may see or hear disturbances. So the clock speed is mentioned in hertz, kilohertz, megahertz and so on. Hertz is the number of cycles per second. So for example, the Z80 on the microprocessor 1 board is clocked at 1.79 megahertz. That are about 1,790,000 cycles per second. The Z80 on the NDR client computer is clocked at 4 MHz. That are 4 million cycles. And last but not least, the 8085 on the Minimax 8085 is clocked at 3.072 MHz. The clock signal is a continuous square wave. You see here, that's one clock cycle. So wave goes up or down, that's one cycle. Let's take for example the machine code 78 in hexadecimal form. That's the equivalent in Z80 assembler load A, B, or in 8085 move A, B. It will just copy the value of B to the accumulator. So number of clock cycles it needs is 4 T-states or clock cycles. That's the same. In this case, both values are equivalent. For example, on the Z80, you can see your M1 cycle, which is the instruction operation code fetch, needs 4 cycles, T1, T2, T3 and T4. I won't go into detail here, but a quick explanation. T1 and T2 is the actual operation code fetch, and T3 and T4 is used for refreshing the dynamic memory. So with T3, T4, the 7-bit refresh address is put on the address bus, and you can't disable it. On the other hand, the 8085 needs also 4 clock cycles. The difference here, there's no refresh address, but the address and the data bus is shared. So you have your own address bus from A8 to A15, but the lower 8 bits are shared with the data bus. So first the low order address is put on the data bus, and after that the data is the shared bus is used for the data exchange. Next example, last one, 3E12, which means in Z80 assembler load accumulator with the value 12. And and on the 8085 it's MVI A,12, which means the exact same thing. Here you can see you need 4 clock states. In this case it's also the same value, but it's not always the case. Sometimes the Z80 is faster or needs less clock times, or the 8085. Quick look. So you have for the 3E, that's the operation code fetch, 4 cycles, and for reading the value you have a memory read cycle, needs another 3 cycles, so together there are 7 cycles needed. Same goes for memory write, I/O operation. Okay, we have the same here for the 8085, also 7 clock states. Okay, how many times can this instruction be executed in a second? That's easy. For example, for 1.79 megahertz, you divide the clock states by 7, because the instruction takes 7 clock states that are around about 255,714 instructions per second. So you can do load A,12 or MVI A,12 255,000 times a second. With 4 megahertz you have 571,000 and so on. The interesting thing is, what is the execution time for this instruction? So for load A,12 or MVI A,12, how do you calculate that? 1 hertz is 1 second to the power of -1. So if you take 1.79 megahertz, you divide 1 divided by 1.79 equals 0.5587 microseconds. So the instruction takes 0.5587 microseconds. With 4 megahertz, that's 0.25 microseconds, and 3.072 megahertz, that's 0.3255 microseconds. I think that's enough theory. Let's jump to the simulator. Before I switch to the simulator, let me show you where to find the values of the t-states. You can find them in the datasheet of your CPU, or here's an example of the Microprocessor 1 board. In the book, in the manual, you can find also a listing of the instructions with their respective t-states here. They have listed every command here, and the final column you will find here the number of t-states. An easier way is to look at the web resource. For example, for Z80, you can find here at the following link a nice table of the Z80 instructions with respective t-states. The Z80 plus M1 is mentioned for the MSX computers. So they include an extra M1 wait cycle. So that depends on your board. You can have additional wait states due to the memory, or I think for the MSX it's it's a standard. So they have put an extra wait state to it, so to use also slower peripheral. You have to take that into account. The same goes for the 8085. You have to check with your board if there are additional wait states due to memory or other peripherals. Here is a resource, for example, for the 8085 t-states. I will put that link too in the description. But now let's switch to the simulator. So let's do our first example. Load B with 12 hexadecimal and C with 78 hexadecimal. You could say load B with 12. So let's check how many t-states that will take. You can type here filter. Load B b, n for value, so that's 7 t-states. And load C with 78. That's also 7 t-states. We can check this. Together 14 t-states and 1, 2, 3, 4 bytes. You would do that on paper here. You would check that in the reference, and there's an easier way. You can use a simulator. You can see here 4 bytes. Loading, executing the first command. You see here clock cycles counter, instruction counter. So step. The first command has loaded 12 into register B. That's one instruction, and it took 7 clock cycles. Next instruction is load C. C is loaded, and also 7 clock cycles, so together 14 clock cycles. There's a way to optimize this. You can use the command load BC and enter a 16-bit value. In this case, B as first value, 12, and C, 78. How many t-states? Load BC and a value, not from memory, but a value 10. And that's 10 t-states and 1, 2, 3 bytes. 1, 2, 3 bytes. Simulation start. Took one instruction and 10 clock cycles, and B and C is loaded. So there's an optimization. If you do another example here, for example, load A with 0, or load A and B with 0. How could you do that? You could say load A 0. That's also 7 t-states. And you could also say load B with 0, but it's easier to do load B, comma A. B, comma register. It's a register, takes only 4 t-states. So together 11 t-states and 1, 2, 3 bytes. 1, 2, 3 bytes. Simulation here. A0, 7 clock cycles. Second command, added 4 to it, 11 clock cycles, and B is 0. But you can optimize this too. So to clear the accumulator, the easiest way is to use exclusive OR A. This will clear the accumulator. XOR, register, that's 4 clock cycles. Load B, comma A, also 4. And together 8 t-states and 2 bytes. 1, 2 bytes. XOR A. A is cleared, 4 clock cycles, and loading B with A is also 0 here, so together 8 t-states. So our next example is a small loop. Load B with 5, our loop here, and in the loop we're just decrementing B and decrement it until B has reached 0. jump on non-zero loop. So here we already know that loading a register with a value takes 7 t-states. Decrementing B takes 4 t-states. And jump on non-zero. And jump on non-zero takes 10 clock cycles. So let's do the math. 7, that's this one here. Then 4 and 10 is 14. So that's 14 times the value of B, that's 5. And yeah, that's 70 plus 7, 77 t-states. And here we have 1, 2, 3, 4, 5, 6 bytes. That's our jump on non-zero, not KP jump. Let's do the test here. 6 bytes. Seven. Next command is decrement, that's 4, should be 11. And jump on non-zero, adding 10 to it, 21, and so on. B is 0, last jump, 77. So how long will it take actually to run this loop? Let's do the math. Suppose our CPU is running at 4 MHz. Let's take the calculator. So 4 MHz, 1 divided by 4 MHz is 0.25 microseconds per cycle. So we have to multiply this by 77 equals 1925. 25 microseconds. We can check this even in the simulator. So let's stop the simulator here. Under options, change clock frequency. So by default it's at 4 MHz. Under options we're doing here enable logging. And let's step through the program. So B is 0, our last jump, and we are stopping the program. When I stop the program, automatically the window pops up with the logging. So you see here every command. And real-time duration took 77 clock cycles, or 19.25 microseconds at 4 MHz. Suppose the thing is running at 1.79 MHz, 1.79, that's 0.5587 microseconds per cycle, multiplied by 77, so it's 4301, what was it, 68, yeah, 69. Let's do this in the simulator. Change clock frequency, 1.79, did it take it? Let's check. Yep. So, simulation start. 0, 1 last, operation, stop, and you see here 43.02 microseconds. Great. Okay, let's do the same example with the relative jump. And the relative jump takes 12 and 7. So here are two values. So if the instruction has to jump to the label, it will use 12 clock cycles. If it doesn't have to jump to the label, it will only use 7 clock cycles. So in this case, if the 0 flag is not set, it will use 12 clock cycles, and if the 0 flag is set, it will only use 7. So 12, 7. Let's do the math here. Here, loading B, 7 plus, and loop here is 4 and 12 is 16. Times 5. That's 80, 87 minus the difference. It's 5, 87, it's 82. And the relative jumps uses 1 byte less, so it's only 5 bytes. Okay, removing logging here. So does only use 5 bytes. So we are at 11 clock cycles. He's doing a jump, adding 12 to it, 23, and so on. So it's 0. So the last jump here will use only 7 states, because 0 flag is 1. 75 and 7 is 82. That's correct. So let's do the math again. 1.79 megahertz, so 1 clock cycle is 0.5587 microseconds long. 82 multiplied with 82, that's 4581. Let's remove this one and enable logging. I have to stop simulator first. Enable logging. So the last jump, stopping the simulator, and what we have here 82 clock cycles, or 45.81 microseconds at 1.79 megahertz. Great. Okay, let's do one last example here. We're using the decrement jump on non-zero command. And it takes 13.8. 13.8. So 7, then 13 times 5, because that's our loop, it's only 13 cycles. So that's 65 minus the difference here, 5. That's 60 plus the 7 here is 67. And it takes only 2 bytes, so even 1 byte less, 4 bytes. stack command jump on non-zero. Okay. Stopped loading, so it takes only 4 bytes. $33. $67 clock cycles, 30, 43. Let's do the math. 1.79 67. Oh my goodness. 67 times, that's 37.43. So it takes less space and it is even faster. So the last example I want to show is actually, I will show it in the next video, but a little teaser here. So we have a serial communication with 300 balls with 8-bit parity none and 1 stop bit. Our CPU is clocked at 1.79 megahertz. So the question is, what should be the delay between the different characters? So what should be the delay between different characters? So in our program I want to call a subfunction delay. So what do we have to put in the subroutine delay? We will cover that in the next video. If you want to watch also the Intel 8085 examples, stay tuned. Otherwise, see you. Bye bye. So let's do our first 8085 example. I will do the same thing as with the Z80 before. Load B with 12 hexadecimal and C with 78 hexadecimal. So you could say move immediate B with 12. That will take move a it's the same value, 7 T states, and move C, 78, also 7 T states. That's together 14 T states and 1, 2, 3, 4 bytes. But there's an easier way to do it. You can use the simulator, so you know it's 4 bytes. And here you have instruction counter and also clock cycle counter. So the first command, load B with 12. B is loaded. You see it was 1 instruction and it took 7 clock cycles. Next instruction, C is loaded and another 7 T states, so together 14 T states. Okay, there's a way to optimize this. You can use the command load extended B with a 16-bit value. First the B, 12, and then C, 78. So that will take LXI. Yeah, I think that's a bad. Oh yeah. 10 clock cycles. take 10 clock cycles and 1, 2, 3 bytes. That's an optimization. 1, 2, 3 bytes. Executing the command. B and C is loaded, and you see here was one instruction and took 10 clock cycles. Next example, load A and B with 0. So there's no command to load accumulator and B together. You can say move immediate A, 0, 7 T states, and you could also say move immediate B, 0, but let's do an optimization here. Move B, A, and the yeah, this listing is not, it's not perfect. I will switch to another table. Okay, I found here a different website. So let's do here move. So register, destination source, it takes only 4 T states. So together 11 T states, and it's 1, 2, 3 bytes. 1, 2, 3 bytes. A loaded with 0, took 7 clock cycles, and the second one, B, is loaded from A. It took 4 clock cycles, so together 11 clock cycles. So there's a way to optimize this. The easiest way to clear the accumulator is doing exclusive OR with register A. So exclusive OR with A. Exclusive OR with register. So you see here the first value is register and the second value is memory. So we take here the first value, that's 4. And the command B, move B, A, also 4 T states, together 8 T states and 2 bytes. 2 bytes. First command, A is cleared, took 4 clock cycles. Second command, B is loaded with A and also 4 clock cycles, so together 8 clock cycles. So let's do another example, a small loop. Loading B with 5 and doing our loop here, decrementing B and decrement it until B reached 0. So jump on non-zero loop. That's it. So we have already learned loading register takes 7 states. Decrementing a register takes 4 states. And jump on non-zero. Jump is 10 and hey, where's conditional jump? Oh boy. The other one, it's 7. It's actually a combination of 10 and 7. I have no good list here. That's weird. So, a normal jump or a jump on a condition is always 10 cycles. and 7 if it doesn't have to jump. So let's do the math here. 7 for loading register B, decrementing it. It's 4 plus 10, that's 14 times B, 5, and minus the last one, it doesn't have to jump, that's a difference, minus 3. So that's 70 plus 7, 77, minus 3 is 74. 74 T-states, and that's 1, 2, 3, 4, 5, 6 bytes. Okay, 6 bytes. Simulation start. 7, decrementing it. 11, jump on 0, adding 10 to it. 21, and so on. So the next jump, because 0 flag is 1, he won't add 10 to it, but only 7. So 74. So how long will it take to run this loop? Suppose our CPU runs at 4 megahertz. Let's take the calculator. So 1 divided by 4 is 0.25 microseconds. So one cycle takes 0.25 microseconds, and we have 74 cycles multiplied by 74. That's 18.5 microseconds. So how can we check that in a simulator? That's easy. Stopping the simulator, checking the clock frequency here. It's at the default is 4 megahertz. Enable logging, simulation start. Stepping through the program, the last jump, stopping the simulator, and it will automatically open an empty window. No, there's a problem with the font. There's the color here, options, where the thing, change color theme, yes, color theme. Let's take Artica, it's fine, Artica is fine. So you see here, here's the command, here's done, so real-time duration, 74 clock cycles, 18.5 microseconds at 4 megahertz. That's great. Suppose I want to calculate if has 3.72 megahertz, so 3.072, that's 0.3255 microseconds per cycle, 74 cycles, multiply it, 240885 microseconds. Change clock frequency, 3.072, simulation start, 0, the last jump, simulation stop, and you see here 2409 microseconds. Okay, so the next example I want to show is for the next video, but I will give you a little teaser. So we have a synchronous serial communication at 300 ports with 8-bit data, parity none, and 1 stop bit. Our CPU is clocked at 3.072 megahertz. So the question is, what should be the delay between the different characters? So in our sub-function I want to call a delay. What do we have to put here? We will cover that in the next video. Thank you for watching. See you. Bye bye.